Flood fill, also called seed fill, is an algorithm that determines the area connected to a given node in a multidimensional array. It is used in the bucket fill tool of paint programs to fill connected, similarly colored areas with a different color, and in games such as Go and Minesweeper for determining which pieces are cleared. When applied on an image to fill a particular bounded area with color, it is also known as boundary fill. The algorithm. The flood fill algorithm takes three parameters: a start node, a target color, and a replacement color. The algorithm looks for all nodes in the array that are connected to the start node by a path of the target color and changes them to the replacement color. There are many ways in which the flood fill algorithm can be structured, but they all make use of a queue or stack data structure, explicitly or implicitly. Depending on whether we consider nodes touching at the corners connected or not, we have two variations, 8-way and 4-way respectively. Stack-based recursive implementation equals, one implicitly stack-based flood fill implementation goes as follows. Flood fill, 1. If target color is equal to replacement color, return. 2. If the color of node is not equal to target color, return. 3. Set the color of node to replacement color. 4. Perform flood fill. Perform flood fill. Perform flood fill. Perform flood fill. 5. Return. Though easy to understand, the implementation of the algorithm used above is impractical in languages and environments where stack space is severely constrained. Alternative implementations equals, an explicitly queue-based implementation is shown in pseudocode below. It is similar to the simple recursive solution, except that instead of making recursive calls, it pushes the nodes onto a queue for consumption. Flood fill, 1. If target color is equal to replacement color, return. 2. Set queue to the empty queue. 3. Add node to the end of queue. 4. While queue is not empty, 5. Set n equal to the first element of queue. 6. Remove first element from queue. 7. If the color of n is equal to target color, 8. Set the color of n to replacement color and mark n as processed. 9. Add west node to end of queue if west has not been processed yet. 10. Add east node to end of queue if east has not been processed yet. 11. Add north node to end of queue if north has not been processed yet. 12. Add south node to end of queue if south has not been processed yet. 13. Return. In order to use the processed flag, all the pixels have to be initialized as unprocessed before calling this algorithm. Most practical implementations use a loop for the west and east directions as an optimization to avoid the overhead of stack or queue management. Flood fill, 1. Set queue to the empty queue. 2. If the color of node is not equal to target color, return. 3. Add node to queue. 4. For each element n of queue, 5. Set w and e equal to n. 6. Move w to the west until the color of the node to the west of w no longer matches target color. 7. Move e to the east until the color of the node to the east of e no longer matches target color. 8. For each node n between w and e, 9. Set the color of n to replacement color. 10. If the color of the node to the north of n is target color, add that node to queue. 11. If the color of the node to the south of n is target color, add that node to queue. 12. Continue looping until queue is exhausted. 13. Return. Adapting the algorithm to use an additional array to store the shape of the region allows generalization to cover fuzzy flood filling, where an element can differ by up to a specified threshold from the source symbol. Using this additional array as an alpha channel allows the edges of the filled region to blend somewhat smoothly with the not filled region. Fixed memory method. A method exists that uses essentially no memory for 4 connected regions by pretending to be a painter trying to paint the region without painting himself into a corner. This is also a method for solving mazes. The 4 pixels making the primary boundary are examined to see what action should be taken. The painter could find themselves in one of several conditions: all 4 boundary pixels are filled. 3 of the boundary pixels are filled. 2 of the boundary pixels are filled. 1 boundary pixel is filled. 0 boundary pixels are filled. Where a path or boundary is to be followed, the right-hand rule is used. The painter follows the region by placing their right hand on the wall and progressing around the edge of the region without removing their hand. For case number 1, the painter paints the pixel the painter is standing upon and stops the algorithm. For case number 2, a path leading out of the area exists. Paint the pixel the painter is standing upon and move in the direction of the open path. For case number 3, the 2 boundary pixels define a path which, if we painted the current pixel, may block us from ever getting back to the other side of the path. We need a mark to define where we are and which direction we are heading to see if we ever get back to exactly the same pixel. If we already created such a mark, then we preserve our previous mark and move to the next pixel following the right-hand rule. A mark is used for the first 2-pixel boundary that is encountered to remember where the passage started and in what direction the painter was moving. If the mark is encountered again and the painter is traveling in the same direction, then the painter knows that it is safe to paint the square with a mark and to continue in the same direction. This is because the pixels on the other side of the mark can be reached and painted in the future. The mark is removed for future use. If the painter encounters the mark but is going in a different direction, then some sort of loop has occurred, which caused the painter to return to the mark. This loop must be eliminated. The mark is picked up, and the painter then proceeds in the direction indicated previously by the mark using the left-hand rule for the boundary. This continues until an intersection is found. Still using the left-hand rule, the painter now searches for a simple passage. Upon finding this 2-pixel boundary path, that pixel is painted. This breaks the loop and allows the algorithm to continue. For case number 4, we need to check the opposite 8 connected corners to see whether they are filled or not. If either or both are filled, then this creates a many-path intersection and cannot be filled. If both are empty, then the current pixel can be painted and the painter can move following the right-hand rule. The algorithm trades time for memory. For simple shapes it is very efficient. However, if the shape is complex with many features, the algorithm spends a large amount of time tracing the edges of the region trying to ensure that all can be painted. This algorithm was first available commercially in 1981 on a Vicom image processing system manufactured by Vicom Systems, Incorporated. The classic recursive flood-fill algorithm was available on this system as well. Pseudocode equals, this is a pseudocode implementation of an optimal fixed memory flood-fill algorithm written in structured English. The variables cur, mark, and mark2 each hold either pixel coordinates or a null value. Note, when mark is set to null, do not erase its previous coordinate value. Keep those coordinates available to be recalled if necessary. Cur-dir, mark-dir, and mark2-dir each hold a direction, backtrack and find loop each hold Boolean values, count is an integer. The algorithm, note, all directions are relative to cur-dir. Set cur to starting pixel, set cur-dir to default direction, clear mark and mark2, set backtrack and find loop to false. While front pixel is empty, move forward, end while. Jump to start. Main loop, move forward, if right pixel is empty, if backtrack is true and find loop is false and either front pixel or left pixel is empty, set find loop to true, end if, turn right, paint, move forward, end if, start, set count to number of non-diagonally adjacent pixels filled, if count is not 4, do, turn right, while front pixel is empty, do, turn left, while front pixel is filled, end if, switch count, case 1, if backtrack is true, set find loop to true, else if find loop is true, if mark is null, restore mark, end if, else if. Front left pixel and back left pixel are both empty, clear mark, fill cur, jump to paint, end if, end case 2, if back pixel is filled, if front left pixel is not filled, clear mark, fill cur, jump to paint, end if, else if mark is not set, set mark to cur, set mark dir to cur dir, clear mark 2, set fin loop and backtrack to false, else, if mark 2 is not set, if cur is at mark, if cur dir is the same as mark dir, clear mark, turn around, fill cur, jump to paint, else. Set backtrack to true, set fin loop to false, set cur dir to mark dir, end if, else if fin loop is true, set mark 2 to cur, set mark 2 dir to cur dir, end if cur is at mark, set cur to mark 2, set cur dir to mark 2 dir, clear mark and mark 2, set backtrack to false, turn around, fill cur, jump to paint, else if cur at mark 2, set mark to cur, set cur dir and mark dir to mark 2 dir, clear mark 2, end if, end case. 3, clear mark, fill cur, jump to paint, end case 4, fill cur, done, end case, end switch, end main loop. Scanline fill. The algorithm can be sped up by filling lines. Instead of pushing each potential future pixel coordinate on the stack, it inspects the neighbor lines to find adjacent segments that may be filled in a future pass. The coordinates of the line segment are pushed on the stack. In most cases this scanline algorithm is at least an order of magnitude faster than the per pixel one. Efficiency. Each pixel is checked once. Vector implementations. Version 0.46 of Inkscape includes a bucket fill tool, giving output similar to ordinary bitmap operations, and indeed using one, the canvas is rendered, a flood fill operation is performed on the selected area and the result is then traced back to a path. It uses the concept of a boundary condition. Large-scale behavior. The primary technique used to control a flood fill will either be data-centric or process-centric. A data-centric approach can use either a stack or a queue to keep track of seed pixels that need to be checked. A process-centric algorithm must necessarily use a stack. A four-way flood fill algorithm that uses the adjacency technique and a queue as its seed pixel store yields an expanding lozenge-shaped fill. Efficiency, 4 pixels checked for each pixel filled. A four-way flood fill algorithm that use the adjacency technique and a stack as its seed pixel store yields a linear fill with gaps filled later behavior. This approach can be particularly seen in older 8-bit computer games, such as those created with Graphic Adventure Creator. Efficiency, 4 pixels checked for each pixel filled. See also, graph traversal, connected component labeling, Dijkstra's algorithm. External links. Didactical JavaScript implementation of scanline polygon fill, by Golim Polo. C program to implement flood fill algorithm, for connected boundary, sample implementations for recursive and non-recursive, classic and scanline flood fill, by Lood van der Ven. C implementation of flood seed fill algorithm from Graphics Gems. BSD-ish, license, by Paul Heckbert. Flash flood fill implementation, by Emanuel Ferranato. Quick fill, an efficient flood fill algorithm, by John Shaw.